Now we're going to talk about operations on sets. There are many times in which we have multiple sets that we would then like to combine or find out what elements they share or whatever. That's the type of operations we're talking about. But first we need to discuss the fact that if we have sets, their elements came from something. So we'd say that S, and some authors would say U, but S is the universe of discourse. That is it's the giant set of things that we draw our sets from. Okay? And so it might be something like S might be the set of real numbers. S might be the set 1, 2, 3, 4. And then if I were, say, if we were using this universe of discourse, if I said then that A was the set 2, 3, we can see that A here is an element of the power set of S, right? Because remember, the power set is all combinations of the elements in the set, and certainly 2, 3 is one of those subsets. So A, of course, is a subset of S, but it's an element of the set of all possible subsets of S, which we call the power set. Okay? So there's several standard operations that we'll use over and over again. So the intersection of A and B, we write like this. It's like an upside down U shape, although it doesn't have like a bar like a normal U would. A B is equal to this. X, where X is an element of A and X is an element of B. That is, it's the set of the shared elements of the two sets A and B. The union of A and B is written this way. It's this shape upside down. So it's not, like I said, it's not this. Okay, it's sort of its own symbol. So some people say it's like a cup. The union is where we combine the elements of A and the elements of B. So if it's in either one of the sets, it'll be part of the union. Whereas if we're talking about the intersection, it has to be a member of both sets. And remember that when we're combining things, we're producing a union. Remember that with sets, we don't care about order, and also we won't have duplicated values. So if A and B had the same elements, the union of them would just be A. Okay, so if A had the elements 2, 3, and B had the elements 2, 3, the union of A and B is still just 2, 3. We have the complement, spelled like this, of A. There's different ways to write this, but this is one of the ways, like A prime. Sorry, this will be this. No. So this says the complement of A is the set of all elements of S in which X here is not an element of A. So take our universe of discourse S and subtract out the elements of A. So if we had this S again and this A, the complement of A would be the 1 and the 4 because I removed the 2 and the 3. Okay? And then we'll write one last thing here, the difference of sets. So difference of A and B is we would typically write like this, A minus B, which is equal to the intersection of A and the complement of B. And sometimes we also write it like this. Okay? So A minus B are the values in A not also in B. Okay. Now the difference here, A minus B, or written this way, these are the two ways you typically see it, but this is how you can produce it. All right. It's also sometimes called the relative complement, whereas this complement would be the absolute complement. All right. So there's some definitions. Now let's look at some examples. So we'll say that S is the set 1, 2, 3, 4, 5, 6, 7, 8. And we'll say A is equal to set 1, 2, 3. B is the set 2, 3, 4. And C is the set 5, 6. Okay? So let's find A union B. Now, one of the things I'm going to use is something called a Venn diagram. And these are very useful for visualizing what you're doing. And so basically we'll draw in the Venn diagram, we'll have typically a circle for each of the sets involved, but arrange those circles such that they show what's happening. So when we're talking about the union of A and B, remember we're talking about the total combined elements. So if I were to say this is A, which has elements 1, 2, and 3, and then B is 2, 3, and 4, we can see the 2 and the 3 are shared by both of them, but A union B would be the set 1, 2, 3, 4. I don't duplicate the 2 and the 3 that are shared by both of them. What about the intersection of A and B? I can use the same diagram, and we see now that will be the 2 and the 3. Remember, the intersection is where they overlap, if there is such an overlap. A minus B. So let me redraw the picture to make it more obvious what we have. So A minus B means we subtract out the shared elements, and that means here A minus B, or we can write like this, it's just the element 1. That's what's left over when you subtract out the part that they share. Okay. What about A union C? 1, 2, 3, 5, 6. So the union is a set 1, 2, 3, 5, 6. And the intersection? Where's the overlap? There is none. So we get the empty set. So in this case, we would say that A and C are disjoint sets. There's a J. All right. And then let's look at what would be the complement of A. All right. So if sometimes you do it as a square or whatever. Some people, lots of times if you're talking about the S, I just do it like this, but there's no real restrictions. Here would be the 1, the 2, the 3. That's the A, right? And then you have the rest of them, 4, 5, 6, 7, 8. So here's S. Here's A's place in S, the universe of discourse. So if I want to find the complement of A, we'll subtract this out, leaving the 4, the 5, the 6, the 7, and the 8. And so the complement of A is the set 4, 5, 6, 7, 8 for this example. And there's our basic operations. And these scale, so you could find the intersection of A, B, and C, the union of A, B, and C, those types of things. Okay, but the Venn diagrams then get a little more challenging. Before we leave, though, let's talk about set identities. Just as you have rules for logic and rules for arithmetic, we also have rules for doing things with sets. Okay, and that's what we call the set identities. So let's say 1A and 1B. The union of A and B is equal to the union of B and A. The intersection of A and B is the intersection of B and A. So we say we have commutativity or commutativity. Okay? This should make sense, right? If we're talking about here's A and B, if we're combining these, does it matter which one we think is on the left, which one's on the right? Not really, right? We also have associativity. So the union of A and B and the union of that with C would be equal to the union of A, sorry, this should just be this cup, with the union of B and C. And same thing for intersections. We have a distributive property. And notice here, if I'm using union here, then this would be intersection. If I'm using intersection here, this would be union. So the way I keep it straight is I think of it as being like the distributive property for real numbers. I mean, that's not really what we're doing, but if we think about it, we don't normally write this. Normally we would say like A times the parentheses B plus C is equal to AB plus AC. But if we think about it, there's a multiplication here, right? So really I have A times B plus C is equal to A times B plus A times C. So the symbol that was here will be between the two parts. I do the same thing here. So intersection here, union here, union here. The union here is used in both places here. Intersection here is used in both places. Okay? We have some identity properties. So if I'd have the union of A with the empty set, that's still just A. The union of A with the universal discourse has to be also A. Or excuse me, would be this would be the intersection. If I have the union of A with S, I would get just S. But if I have the intersection of A with S, that's the parts they overlap on, but they only overlap where A happens to be. So it's also A. So we say this is identity properties. So the union of A with the complement of A has to be everything. That's S. But the intersection of A with its complement, they can't share any elements. Because remember, the complement of A is everything in S that's not in A. So there can't be any overlap. Okay? So those are called complements. Right. And then let's also show that we can have De Morgan's laws. There's many more than this. If you look for set identities, online, you'll find more rules than what I've written here. All right? But we can have De Morgan's. So if I have the union, that's a union, of A and B, and take the complement of that, that would be the intersection of the complement of A with the complement of B. And we can do the same thing with intersections. All right. So like I said, there are other rules. You can look these up, but I think these are the ones that largely get you what you need. Because what we'll do in a future video is we'll prove certain relationships. So if we say, like I did earlier, I said, well, what's the difference of A and B? Well, you can find it by taking the intersection of A and the complement of B. How do you prove that? Well, we can use these identities to reason our way through it, just like we would if these were properties of real numbers or logic, like we've seen in previous videos or whatever. So they're useful for that. But like I said, you can find these and many more if you search for set identities online.